pretty cool t-shirts with me. Then at the end, please, you who still are standing, come get your t-shirt. It says, "My data is bigger than yours." Because that's what this industry is about. This industry is not about modeling. This industry is about models, yes, a little, as much as the internet is about apps, or the media is about apps. It's just a tiny little fraction of what we're doing here. And I think that particularly understanding about electronics is fundamentally important. So why I've chosen this picture here first, that's my Twitter handle, so I talk about this kind of thing in Twitter as well, so if you're interested, you might enjoy it. When I was 6 years old, my mom brought home this particular machine, Big 20. Obviously it's not this exact machine, but it was that exact model. And I still remember that day, 1981, I believe, 1982, I turned on the power switch and the blue screen came up in the TV and it was quite a magical moment. And actually still today, often when we solve problems, I feel exactly like I did feel that time. And that was about the time when I was 6, when I realized that I didn't remember a good chunk of my life. And I was very surprised. I was sitting in the car and suddenly I realized, hold on, I don't have a clue what I did for the first few years of my life. And then I thought about what was my earliest memory. And my earliest memory was lying down in the bed at night, not being able to sleep, and counting the objects in my curtains. And actually, I don't know if it was this exact curtain, but that is the way I remember it. Then, in 1991, we had been playing Dungeons and Dragons for many, many long years. Long years. Anybody here played Dungeons and Dragons knows that those are long years. Because you don't sleep, you just play, and you don't do anything else. And in 1991, we were anticipating the release of a new game called Cyberpunk, which was based on William Gibson's cyberpunk genre. And we were actually waiting in the front of the store. We were the only people waiting in front of the store. So, you know, people used to do this already before iPhones. And this allowed us to experience things in a completely different way that we had imagined. We were able to create a world of the future. The world where man and machine live in some kind of symbiotic cooperation, if you may. And just to kind of summarize this early phase of my life, I think that I am one of the lucky ones that actually did survive. And thanks to that, when I was, I think I was 18, 19, 20, when the internet came in the mid-90s, I didn't find school very appealing. I was in high school, so I dropped out. And we ended up building later that year, over that year and the following year, the first e-commerce solution in Finland with 4,500 products, modern really e-commerce solution, and that's the actual look and feel of the first e-commerce solution in Finland. We were able to convince them that this was the right kind of design for me. So this led me to founding a bunch of companies, 2 of which are here in Singapore. One is Statsic, deals with very interesting things around social data, and then MediaCorp, a company that deals with programmatic media data. And also I'm a member of the 10X Computer Club. It's a multidisciplinary, kind of a special interest group. There's about 10 of us. We have some of the top universities in the world represented there, MIT, Cambridge, and so on. We have people from astrophysics, chemical engineering, and then we have a bunch of other computer geeks like myself. And we get together and we talk about computing in the kind of context that I'm going to talk about it right now. And I have 3 key points that I would like you to have as a takeaway going out from here. One is that data science is much more than just models. And then that hardware is really great, but software is not so great. And we can do a lot more than we think about these things. So I promised lean science, lean data science, so let's first define what lean means to me. So I'm going to make many bold claims during this talk, and I'm not asking you to believe any of actually, I would encourage you not to believe any of it. But what I would encourage you to do is to contemplate on it. Challenge your current thinking with it. Actually, I'd be disappointed if there was even one single point that any of you would take from here and say, yeah, I believe that. Please do not believe anything that I say. These are only claims that I make, and I make a lot of claims. If you knew me, you'd know that. So now, when we say lean, we are thinking kind of like here is, meat that is not that lean, and then here is meat that is lean. Well, I'd like to think about it in a little different way. So almost in the context of food, I would like to think that lean is eating a raw vegan diet. Not that I like hamburgers and stuff, but I think that's a kind of analogy that explains what lean means for me. Most importantly, lean, no matter is it lean startup, lean science, whatever it is, it's really an intersection of commercial innovation and scientific method. It's those two things coming together in one nice package. They work together. So what's data science? I bet that if there was a survey and I'd ask all of you, do you know what data science is? And there was a box, a Boolean, box, everyone would say, yes, I know. But then we would sit down and we would start to dissect it, nobody would know. And I don't know either. But what I'm going to do, I'm going to make my claim on what data science is. And then if we meet in 6 months, I probably changed my mind already. Okay, first, it is fundamentally the game of moving from pure luck to pure skill. So instead of just throwing coins, just throwing dices, we start to slowly make our way through the luck-skill continuum until we reach a satisfactory level. Another way of looking at this is that there is a theoretical aspect and there is a practical aspect, just like in any science, right? And it's very important now to say all the results are actually there. I doubt that there is anybody in this room, if this is really a data science meetup, who is actually delivering real results. Those are different people who then take our work and actually make something out of it. And I want you to realize this so you don't feel bad about it. Science has always been like this. There are theorists and there are practitioners. And for myself, I used to be a practitioner, but I actually enjoy to be a theorist more. And I think that that's what we need now. We need more and more commitment to this theoretical aspect. And more importantly, you see there is external, which is kind of, logic or probability that is not already there. So we come up with some kind of a construct, either a logic construct or probabilistic construct that is not there yet. Okay, that's the external part, and that's what people associate with data science. But then there is the internal aspect, and you see that's where all the cost is, or great majority of the cost is. And that's data, CPU, memory, disk, bandwidth, programming people. And I'm going to be talking about that. And why I'm going to be talking about that, and remember now, don't please slay me if this is not appropriate, because again, I'm a high school dropout. I'm nowhere near as smart as the Swedish guy or the guy who talked before me.
I'm a dropout too, by the way.
Say again?
I am a dropout too. So.
But you're from Sweden, huh?
Yes, but that's a geographical thing. I mean, we're just smarter by nature.
So, and by the way, one thing that the Swedish people don't know is that about 50% of them are genetically coming from Finland. That's okay, and especially our friend here.
That's the other half.
Of a Finnish
It's the other half, so I'm fine.
Okay, so basically what I'm saying here is that external aspect of data science is a zero-sum game, because we are competing for a result with someone, whereas the internal aspect is not. Which means, theoretically speaking, we can infinitely gain more. So I want you to really think about this. So, I'm not going to read this, but that's my definition for what lean data science is. Okay? So basically, just to dissect it a little, I'm going to dissect it in a few different ways to give few different looks into what this really is about. So okay, we have theory, right? you can't really do anything without theory. You don't have strong theory, please don't tell to me about that, about your models or anything. Any true scientist bases everything on theory and then works on top of that. Then, on top of theory, we actually create some kind of a hardware construct. On top of that hardware construct, we have a software construct. And then on top of that, we run the models. But remember again, these four are not a result yet. We need the business guys or the practitioners to then go and take our work and drive a result from it. So here's a little bit more deeper look into it. These are the different layers that we've identified in terms of arrangements. So basically, all of this is about arrangements. The internal data science is about arranging things. It's about arranging bits. It's about arranging pieces of code. It's about arranging programs, software. It's about arranging hardware, about machines, and then the grids of the machines. And what's interesting here is, now these dots represent the different layers. They all contribute to each other, and they all circle this cost to gain factor, which we really are very much interested for. This is our main thing that we are looking at, is how do we continuously improve our cost to gain? And it really comes from deeply looking at all of these different aspects. And maybe we choose our discipline. Maybe we don't become great in all of this. I'm just a computer geek, basically, so I like this kind of, general, very broad approach. But some of you may not be from that kind of computer background, so you might say, you know what, I'm going to just focus on one or two and I'm going to be great in those. So basically, from here, cost to gain. Okay, so the major cost factors here are, on the top you have kind of people who design, build, quality, and maintain. On the bottom, you have processing units. You have, there's a typo there. You have RAM, and then you have your spinning disks and SSDs, and then you have your downloads and uploads. So really the question then is, where is the theoretical minimum here? What is the theoretical minimum? Because that's what we're really going for, right? We're looking for a theoretical minimum. So I want you to, if there is one thing, because I'm showing you a lot of different kind of structures, I did say ontology in the promise for this talk, so I try to deliver for that. And ontology is, of course, about lists and structures. So this is the one that I really want you to think about. In the middle, we have performance. So the previous guy here was talking about that it's all about throughput, but it's not all about throughput in our world. It might be under C, I don't understand that at all, but if electricity is a factor, operation per watt is as important, if not more important, than just looking at throughput. And we can talk about that in a bit more. Then on the black boxes, I have kind of the fundamental computing pieces. Computability, security, complexity, programmability, and reliability. Those are the factors that it'll be an interplay of all those factors, what happens in the middle. And then the gray boxes are kind of the people aspect, the user aspect. You have a system that is used by people, they're interested with privacy, there are sensor data, there is accessibility, and there is usability factors. So at this stage, I want to summarize to you, data is not value. That's very important to understand. Data definitely is not value. Data is cost. It is the opposite of value. It can be made into value, and here is a thinking framework that MediaQuark in programmatic media has used. So basically you have data for planning, you have data for targeting, you have data for marketplace, you have data as a balance sheet asset. So you basically have monetary things, you have internal things, external things, and you have inside things. And the way we do this, of course, we use logic and probability, which comes in many shapes and forms. And basically, the simple way to look at it is that the randomness and the possibilities you get from that approach, they go more or less together. And we can have all kinds of intelligence. We have intelligence that has very little randomness and also has very little possibilities, but it's probably going to do a pretty good job. It's going to be pretty predictable. But then on the other hand, we have things like us human that are not very predictable and are very random, but also we have many possibilities. So, good. Actually, this is the topic that I really want to talk about here. This is the thing that I have more or less spent all my life with. Since a 6-year-old kid, I'm now 38. 32 years, I every day somehow interact with computer, with a vision of the future, with an idea of how much more we could do with the computers. Computing is broken. And it's not because of the hardware. It's because of this guy. Because no matter how nerdy, how geeky, even if you never did anything except program, there is no way you can deal with even a small fraction of the true complexity of this. A modern processor does 2-3 billion clock cycles a second. Every second the clock ticks 2-3 billion times. And at every single cycle, a 64-bit block goes through. This is in optimal conditions. So, anybody want to take a stab how many zeros are on the universe of variety that 64-bit block represents? Anybody? I think it's about 1 trillion. It's somewhere there, but it's big. So why computing is really important and why I am clearly very affectionate about this topic is not because of data modeling, it's because of computers. So I believe, and I think a lot of other people believe, and I believe that most of you will believe as well, that advancements in computing will benefit advancements in science. A lot of the significant research, dark matter, evolutionary biology, a lot of these different things, they depend on computing. And you go to any research facility, including here, the supercomputers are fully booked. And you go to ask from any research agent, do you have enough supercomputing time? None of them have enough well, some, there are exceptions. But most of them will say, no, I'd love to have more. Actually, this is slowing down our research. And what's really cool here, that they really work together. Computing efficiency improves advancements in science. And then advancements in science improve computing efficiency, or have the propensity to act as a cause. So it is just this self-enforcing cycle. I wanted to say vicious cycle, but it is really, I believe, for the greater good of humanity, so I think that would be a bad word. So how about if we step it up a notch, or a few notch, and then remember again, this is not a zero-sum game. Most of our resources, most of the smart people, they play the stock market, they play marketing, they do all these different things that are all zero-sum games. So basically, two smart people play against each other. How about if these smart people play positive-sum games? Games that they can both win in without the other losing. But instead of talking about this, we talk about big data. Everyone's having the big data Kool-Aid. And why? It's because the big IT and the big consultancy, they're very good at getting people to drink Kool-Aid. Whatever Kool-Aid they want people to drink. In the 1990s, it was the integration. At some point, 95 of all IT budgets were going to integration. Then 5 years later, you went to these big corporates and it was a huge mess. So they show us slides like this. It's going to be trillion devices and blah, 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 blah. And everybody's drinking the Kool-Aid. Why don't they show us this kind of slides? They like to show us maybe the top part that the Moore's law is going up. Yeah, the transistors are coming denser and denser and denser. But what they forget to tell us that there's another law that has gone together with Moore's law, which is no longer going together with Moore's law, which correlates with actual throughput, which correlates with actual computational efficiency. Hard disks are becoming cheaper, yeah, sure, so let's just store all the data we can. But one thing that we forget is that a box, a standard box, if it's running on full power, or if it's on idle, there is only a 35%, it's from 100% energy consumption to 65% energy consumption. because it's not the box that takes the energy. It's the cooling of the space. It's everything that goes together with it. And energy, we don't have abundant energy. And energy prices are continuously increasing, and they are predicted to continue to increase. And then the growth of data. So the growth of data alone negates whatever happens up there, and then there's the electricity that will come and do a quick one on us. So based on Gartner, between 05 and 25, there will be a 16-fold increase in DC consumption. So obviously, DC consumption is coming from everybody wanting to do their taxis at Sunday 2:30 a.m. or watching a personalized news feed or whatever it is. But you know what? That's not even the dark horse. The dark horse is the bandwidth. So the big problem is not the electricity. The big problem is the bandwidth. Nobody really knows what's going to happen with bandwidth. And when you talk with people, both from commerce and academia, and we have this aspect represented in the 10x Computer Club, they speak very openly about how what we're doing now is not going to last. Because you know what? All of the data that we transfer, even the pipes could do it, takes a lot of energy. Energy we do not have. Energy that is becoming more and more and more expensive. So I'm going to use an ad tech stack here as an example. Roughly, this is just a very rough indication of how much money goes into processing, how much money goes to RAM, how much money goes to hard disks, and how much money goes to bandwidth. So I think that's something interesting to think about. This one I am going to read from the screen. Big data, the activity of storing, processing, and moving a lot of data for a long time. That's about right, yeah? That's kind of a thing that's being sold to us as what big data is. So now remember, data is cost, so big data is big bucks. But it's not big bucks for us. It's big bucks for IBM. It's big bucks for McKinsey. It's big bucks for those two stakeholder groups that we discussed earlier. Big IT, big consultancy. They have worked together very nicely over the past 20 years. When they couldn't sell IT anymore, when IT started to become less sexier, they came up with two very interesting buzzwords, cloud and big data. Those are synonymous with IT. In IBM, they talked about IT in the 1990s and early 2000s. Now those exact same people, they talk about cloud and big data. So it's a kind of a Ponzi scheme, almost, using a mathematical reference. And really the problem is that investment drives scale, not the other way around. So it's the street, the money from the street, that's driving innovation around scale. But it's not innovation, it's just burning money. In the ad tech industry, all these companies get listed now, and almost none of them make money. Their books look terrible. I mean, you look at these companies that are being listed, and no sensible investor would ever put their money into a company like that. So I want to introduce a different concept, just enough data, and again, I'm just going to very boringly read from there. The activity of storing, processing, and moving data as close to the theoretical efficiency maximum as possible. So there's a difference there. There is a semantic difference there. So now I want to talk about something practical, so you are not going to go away from here just listen to somebody rant about all these problems, but you can see that we can do something. We can change ourselves, and then we can change the world. And the really important thing is to think differently. So first, Hello World. Who has ever done a Hello World program? Can you raise your hands? Hello World, great. So my associate from 10 years, we've had the privilege of working together with, for 10 years, and I highly recommend for you to do that. If you are serious about science, find associates that you can work with until the day you die. I'm not kidding you. There is no way you can ever alone do what you can do with great associates. Find one first, then you find a third one. Now we are looking for a third one, for someone who could join us, and then we will one day look for a fourth one and fifth one. And then hopefully one day, long from now, we've established a kind of a lineage that cannot die. Then it's not dependent on us anymore. So hello world, this is a very simple basic program, right? This is written in C, okay? So that's just written in C using string. Who knows what is string? Yeah, everybody knows what is string, who knows C. Yeah, okay, good. So here, my dear brother Sasi was kind enough to give me an example where he did it out of string. Anybody want to guess what's the performance increase? It's over 100 times. Okay? So what I'm showing to you here, now I move to the next example. Now my examples are going to get gradually more complicated. I'm going to show you a few different examples, each representing one aspect of computational efficiency. What's that there? That's a 200 times magnified, on my screen it's 200 times magnified, here it's much more, of one single pixel. That's million of those same pixels. That's actually a totally black screen. It's filled with those same pixels. So that's the difference, the actual relative difference between storing data for 1 year or storing data for 1 second. And trust me, after doing multiple analytics data startups, most data you don't need to store even for a second. Actually, once you move into, you know, the early step is to move to pure memory-based. You don't do spinning disk or SSD anymore at all. You just do memory. But what we are doing now is we are moving away from memory to just pure cache computing. And the lower in the cache you can run things, then more you are really talking about things just absolutely passing through. And we're talking then having that data in our system for a 5 nanosecond period. Okay? So here's a very practical commercial example for you now. We have, with MediaQuark, we have a media planning tool for programmatic media traders, and we had URL data. So we had basically 2 million of this kind of, you know, sites in our database. And we wanted to see how we could reduce it. We were doing n-gram analysis, very simple thing. So we had an n-gram analysis under there to match domain names with each other. So we wanted to retain all of the logic of the n-gram analysis with those 2 million websites, but we wanted to make it smaller. So we made it from 100 megabytes to 0.7 megabytes. And again, we retained 100% of the n-gram logic there, 100%. Yet we reduced the data to about 130x. And by the way, that was the first time we ever tried it. We had theoretically been speaking about it for years already, but this was our first practical experiment. Right now, we have reached a far superior level to this. We can take almost any data in almost any system that we are aware of and reduce it somewhere in the between of 100 to 1000x. And how do we do it? We do it very simply. Anyone know what this represents, or this? Yeah? The electronics guys will know at least immediately. So these are, of course, the basic units of logic. That's why it's so important to know the basics of electronics, because that's what computers fundamentally are. So that's simply what we did. We just reduced everything to the level of the gates, because that's what computing is about. So now I'm going to give an example of a larger industry problem in the ad tech industry. And this doesn't reflect at all what's happening in the stack. This is a very layman simplified version of what. Basically, there is a guy who takes his browser, sees a Pumpkinville ad on the Pumpkin site, and then, you know, there is a little piece of tag in that ad. Actually, there's about 100 or 200 every time you see the ad. And then all those hundreds of tags, they fire up on hundreds of servers all around the world, and all of them send empty GIFs. God forbid. Empty GIF, turns out, is 24 bytes in size. So all of these people are sending these empty GIFs when they could be sending just an empty JavaScript file, which is 0, not 24. So every time anybody, trillions of times, literally trillions of times a month, every time anybody sees an ad, a lot of those people are still using these empty GIFs. So when we started to analyze this stack, this particular aspect, that was the first insight we had. Okay? So we took that away and we started to save a lot of money. We just simply replaced the empty GIF with an empty JavaScript, and that's it. Then the next thing we looked at was the Apache server. Okay, we had taken this for granted. We were the internet guys. You know, I started one of the first internet technology companies in Europe in mid-90s. So I'd been, you know, a devoted follower of Apache HTTP server. Turns out it's a piece of shit. Again, sorry. Yes, luckily there's no children in the room or your teachers. So now, or the lecturers or whatever you call it, turns out that of course, like everything else, is just this one generic bloated pile of garbage. Actually, for programmers, garbage is a very familiar term. So I really mean garbage, but it's not the kind of garbage you have, lurking in the memory. The whole thing is garbage. There are individual bits and pieces there that you absolutely need to use. But you don't need to load the entire stack every time you send an empty JavaScript. Especially when 100 or 200 people are doing it every time, So you start to see hopefully a pattern here with the energy consumption, bandwidth, the way we are doing things, these fundamental technologies, right? Okay, well, we didn't stop there. We went through one step down, and turns out it's even worse. It's this bundle of every single thing you can imagine, watching videos on your computer, loading files, going to IRC, all these things that nobody even does anymore, and they all have priorities. So every time the TCP IP is loaded, all of that is loaded. And it actually checks on your computer, all these things, are you doing this, are you doing, every single time. Just so we can serve this one empty thing, right? So that was the third thing. But unfortunately, what I found is something even worse. In the university you learn Linux is the shit. Yeah, actually, it is the shit. It literally is that. So I want you to have Linux kernel map. Anyone know Linux kernel map? Yeah, right. So I want you to look at the networking stack. Every time anything goes through the network, this is the maze it will have to travel. So in the 1980s, there was a movement called microkernel movement, which was an application-specific kernel. Very, very tiny. But for some reason, that movement died out. It does not exist anymore. You go to the Wikipedia page of microkernel, and they will actually say it there. It has died out. In the late 80s, it was entirely dropped. Because we went to the world of generic computing. Everybody needed to do everything suddenly. So why is this a big problem? Well, fundamentally speaking, because this here represents the top 500 supercomputers by operating system. Yeah? So almost all of the world's supercomputing runs on Linux. Not on microkernel systems that are specifically made for dark matter research, made for genetics research, or whatever your field of interest might be. So I think this is my final example, and then we will conclude this talk. So this is us in 2008. Anybody who's played with Apache servers knows that at about 1,000 per second, something just happens. Something goes wrong. The box starts to die. And then we were able to find a way how we could do 5,000 connections per second. Yeah, and that's where we were left. Then this year we had a pretty substantial breakthrough. We went from 5,000 to 20,000, but then one month later we went to 1 million. Right now, we are, honestly speaking, with MediaQuark, the team is running about 500,000 per second on a single box. It's an Amazon instance that costs $300 a month. So I think that that's pretty substantial improvement for anybody who understands about trafficking connections of any kind. And most important thing is that we have now already a theoretical finding that allows us to do 1 billion per box per second. Okay? So now this guy is Robert Graham. Anybody here done any hacking ever? No, of course not. How would anybody have done any hacking? So Robert Graham is a bit of a thing in the hacking world. He created a little piece of software called Black Ice. And Black Ice was a kind of a sexy thing among hackers and role-playing crowd. I mean the cyberpunk crowd. So there is a video online where Robert Graham talks about the last example that I was talking here, and talks about a very interesting network package management solution called PF Ring. And this video has 257 views. In this video, he lays it out entirely how you can 1000x your server performance, but it has 257 views. How about that? So I think that that's kind of pretty descriptive of what's going on here. So just to kind of, before we go to the kind of closing note and my key learnings, just to summarize a little bit. CPU is super fast. It's as fast as the clock speed, right? It's as fast as the cycle, clock cycles. If you have 2 billion clock cycles, that's your processor speed. L1 cache. Cache is like a waterfall, basically. So there's a tiny, tiny little piece of L1 cache, which is as fast as the CPU. There is no bus. It doesn't go through a gate, a port of some kind, like this door, for those who don't know exactly what bus is. Then we go into the backside bus, L2, L3. They are running from a bus which is maybe, I guess it's about a 50 nanosecond, 100 nanosecond. It's hard to get exact information on this because all of it is very theoretical. Computing is not used at that level very efficiently until now. Then we go to, for me, this is where efficient computing ends. Once you are in RAM, you're gone. That's no longer efficient computing. Yes, sometimes, obviously, you need to... The problem is not that RAM is super slow. DDR4 is 3 GT per second, gigatransfer per second, which is not the same as gigabyte per second for those who don't know. Now, what makes it problematic is that the fact that something is in memory means that the cache is full. Fundamentally speaking, that is the reason for us. Only reason why we would have something in memory is because our cache is full. And when our cache is full, it means we have failed. It means we no longer are living up to the promise of the computing. And this goes back to the beginning, talking about grids and so on. So cache is very expensive, right? But it's not if you stack up microcontrollers. Imagine stacking up 1,000 Raspberry Pis. It'll cost you $25,000, right? You'll probably get a good discount, so let's say you'll get them for $20,000. You can stack them up together with Lego blocks or whatever you want. That's up to you. That's a gigabyte of cache. Do you have any idea how much a gigabyte of cache costs in supercomputing world? Not only that, it's a single processor system, right? Now, you can't just go and do that because you need some kind of a system that manages the cache load, makes it appear as if it's just one cache. And that's a really, really, really difficult computing problem. So, you can't just go home and build it, but theoretically speaking, this possibility is there. So imagine, we've talked about now reducing data 100-fold just like that. We've talked about many different aspects where we can take these 100x gains. Any which of those you want to take? 100x, 100x, 100x? Yeah, even I know that's a million. That's million x. Okay? So how do we move to this wall? How do we move to the million x computing wall? Well, we need to realize something fundamentally important, that humans are good with human stuff. Okay? And machines are good with machine stuff. And we often forget it, that this is the case. And when we forget it, what comes out is rainbow pooping unicorns. And there is a whole lot of those going around these days. People seem to like unicorns and rainbows. So what's better than putting those two together, right? Yeah. So we like those things. But there are also great examples of us not forgetting them. Look at the financial markets. Think about what it takes. So for example, there's one person in this room that I have a deep respect for, who was running during the bust an algorithmic, purely algorithmic fund that didn't lose money even when the markets went down. Think about what kind of harmony of man and machine is required for such a feat. We took man, it could be in fake moon landing, I don't know, I'm not so much into conspiracy theories, but I assume man went into the moon. And even if we didn't, we've done some pretty impressive stuff in space with computers that were built in the 50s and 60s or something. Yeah? And also, we've broken down the human genome to a pretty impressive level already. These are all examples of what happens when we realize that machines are good with machine stuff and humans are good with human stuff. We're really great at coming up with ideas, but we're really, really crappy at executing them. Machines can't think for their life, but they're very good at execution, and we need to realize this. Okay, now it's maybe 2 or 3 more minutes, and then you are free, I want to just end with the key learnings. I want you to take a moment and just let that sink in. That's the most important single finding over the years of unproven research. The only way to truly know anything is through knowing the knower. Because unless you know the knower, how can you know anything that knower is supposedly knowing? Right? There is a logic error there. Yes? Anybody who works with computers and logic gets that, yeah? That's pretty simple. So, why it's important? You know, 2,000 years ago, every scientist was a philosopher. Every single one of them. 100 years ago, all the great scientists were philosophers. And today, our idea of science is a celebrity chef making food, you know, steam or what, I don't know what they're doing, but, you know, it looks scientific, kind of. But there is also a very important individual part here, which I want you to think about. Just from your own selfish standpoint. If you don't know yourself and you are trapped in thinking that you are isolated from this world and you are some kind of an independently existing self that is separate from everything else, then all the problems of the world will look really big. Any small problem I throw upon you, it feels that it's coming from the world and you don't know how to deal with that. But if you can establish a more substantial view of yourself through the means of knowing the knower gradually, then none of the problems will feel big. There are small, tiny little things that arise within our own being. No matter what the problems are, they all become tiny. And when they are tiny, they don't intimidate anymore. And when they don't intimidate, they become fun. You wake up in the morning and you're really happy that you can deal with those kinds of mind-boggling problems. So how do you do that? How do you know the knower? Well, you got to practice. You're not going to learn it from books. Yeah, you have to learn something from books as well, but you have to practice. And fundamentally, for me and for some of my associates and my brothers, it means to meditate. And my understanding of meditation is very limited. So I'm going to share with you what I understand about meditation, which is very practical. First, before you've ever meditated, before you've established that practice, it is actually like you're in a tunnel. You think you are awake, but you actually never are. I mean, I'm sad to say it, but that was my experience. And I know many very, very intelligent people, including people who are in this room right now, who've had this exactly same experience. Then you start to establish your practice, and slowly, slowly, there start to be gaps in that tunnel. And slowly, 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 the tunnel starts to dissolve. And when the tunnel starts to dissolve, well, then it becomes much more clearer what you really are. Basically, it is a practice of coming from an iron cauldron, an iron cast thing that lets nothing through, which the mind is. We are trained in that way, to a sieve that just passes everything through. And then last but not least, we have to really be kind to one another. We have to learn that only by helping each other and only by making a commitment to somehow, somehow take it as our responsibility to make everyone's lives better, only then I think we are in a position to solve real problems. Were they computing problems or whatever it is, because unless you approach life in that way, it's always about you. It's always about how you can make more money, how you can get ahead, or how people will respect you, or whatever, and no real science happens in that mindset. Yeah? And I want to illustrate that in a very simple mathematical example. Imagine now that you are left in a deserted island. There's only 5 people left in the world, 6 people left in the world, you and 5 others. Now, before anything else, there is a vote. You can vote for one or other. You can vote for a system where everybody works for each other, or a system where everybody works for themselves. So you think about that, which one you would vote for, and which one do you think that would work better. So now, if you want to learn more about these kinds of things, the 10x Computer Club has a blog, Autonomio, and there is my personal website where you can find some articles and some other stuff that relates to this talk. There's a link section there, so you can check out some classic articles on computing that really inspired us. And that's my Twitter handle again. And also, for those who are interested in working in a very exciting field, mediaquark.com/datascience, and also my Swedish friend here, iota.com, both fantastic companies dealing with insanely exciting data problems, and have some absolutely magnificent people working in those teams. So I highly recommend you to look into the internship and career opportunities within both of those companies. Actually, there is one more company that I almost forgot, which is called Scream, SQREEM, which is doing something pretty cool. But I won't go more into that detail. And I want to leave you with a quote that has been our guiding principle for the past 10 years. Thank you very much.